If we look at the relationship between volume and temperature of gas, this is called Charles' law. And if we take a constant volume container, such as a constant pressure container, such as a balloon, where the volume is allowed to change, we heat a balloon, it gets bigger, it swells up. If we cool down a balloon, it gets smaller, it shrinks down. So temperature and volume are directly proportional to each other. That would mean that volume is equal to temperature times some type of constant. And this temperature is the absolute temperature, the Kelvin scale. So if we take this volume is equal to temperature times a constant divided by temperature, we get the ratio of volume over temperature is equal to a constant. We could do it the other way. We could do volume divided by temperature. Temperature over volume would also be equal to a constant. So they're both equal to a constant. Volume over temperature is equal to a constant. Temperature over volume is equal to a constant. So we tend to write volume over temperature is equal to a constant. And if we have one container of gas at constant pressure, we can use volume temperature at one point to help us predict volume or temperature at the other point. So our initial volume divided by temperature is equal to our final volume divided by temperature. Again, this has to be the absolute temperature scale. Celsius calling temperature 0 at freezing point of water is not appropriate because there's still energy in ice water. So we have to use the absolute temperature scale, the Kelvin scale, because at 0 Kelvin there is no free energy, no energy left to share among anything else. And at absolute 0 Kelvin, which is also a negative 273.15 degrees Celsius. This is the coldest temperature possible, theoretically. We have not gone past it. We've gotten very close to it. We've gotten down to a millionth of a degree of a Kelvin. At 0 Kelvin, the atoms, molecules would be in their lowest temperature possible. There might be some base vibration or absolutely no vibration whatsoever. But the objects would not have any heat to give to anything else. If we look at the relationship of a volume of gas to the number of moles of gas, this is called Avogadro's law. And if we look at a balloon, we put gas in a balloon, the balloon gets bigger. We see that volume is directly proportional to amount of gas. Well, it turns out that the amount of gas is going to be measured in moles. So it won't be measured anything else, no mass, just moles of the gas. So we end up finding that our volume is directly proportional to moles of gas. So we can write volume equals moles times a constant, a proportionality constant. If we are looking at gases that have the same temperature and pressure, we can use this relationship, Avogadro's law, to predict how much moles we need to get a particular volume. So we can use an initial moles divided by volumes to help us to calculate a final moles divided by volumes. If we take three gas laws, Boyle's law, pressure times volume, Charles' law, volume divided by temperature, and Gay-Lussac's law, pressure divided by temperature, are all equal to a constant. Combine those three laws together, we get the combined gas law. Pressure times volume divided by temperature is equal to a constant when we have a constant number of moles. So this is essentially proportional to number of moles of gas. So we got pressure times volume divided by temperature will be constant at constant moles, so it's also equal to a final pressure times volume divided by temperature. So if we have these three properties changing from initial set of conditions, we can use this equation to help us to calculate the final set of conditions. And of course we need to know two of the final to determine the third of the final. And of course, again, temperature has to be in Kelvin. For all gas laws, gas properties, temperature has to be in Kelvin. Well, in this relationship here, we got PV over T was proportional to moles. So if we multiply that T across, we get PV is going to be moles times temperature, and then we have our proportionality constant. In this case, we're using R to represent our proportionality constant. We call that the ideal gas constant. Ideal gas constant has a variety of values depending on the units that are used with it, and it's used in a variety of properties besides just the gas law in this case. So to simplify life, we tend to just use one R, ideal gas law, ideal gas constant for this law. For the ideal gas law, which is 0.08206, with units of liters atmospheres per mole Kelvin. So what this means is that in the ideal gas law, the relationship between all our four properties, PV equals nRT, pressure times volume equals moles times gas constant times temperature. So for the ideal gas constant, it means that we should use all the time liters for volume, atmospheres for pressure, well, moles has to be moles, and then temperature is going to have to be Kelvin. So we need liters and atmospheres for our volume and pressure in the ideal gas law. We will be using another version of the ideal gas constant for energy, but we're not going to use that one in the ideal gas law. So PV equals nRT is the ideal gas law. It works for all ideal gases, which are gases that can be described by this equation without concern about the identity of the gas. And this would be called a equation state, which means that it describes a condition without concern of how we got to that particular condition. So conditions are states. So it describes a particular state, condition, without concern of how we got there. This has four variables in there, PV, R, PV, and T. So we need three of these variables to get the fourth. And there's no initial and final set of conditions, so we just want three variables, and we'll calculate the fourth with the ideal gas law. If we see a change of conditions for pressure, volume, or temperature, we're going to think the combined gas law. If we have three properties, no change of conditions, there's three properties, then it's the ideal gas law. We do have gases that do not obey this law, or we can get to conditions where this law is failed. And where those tend to occur are at high pressures and low temperatures. So under high pressures and low temperatures, this equation tends to fail, or the calculated value does not match the measured value sufficiently. And we have a way to correct it later on that will depend upon the identity of the gases present. Since gases vary tremendously in terms of property, depending on pressure and temperature, to simplify our life, we like our tables of data on gases to be comparable to each other. So we tend to use a standard temperature and pressure. Standard temperature and pressure is abbreviated STP, and the reference temperature is freezing point of water, 0 degrees Celsius or 273.15 Kelvin. We have our habit of writing things in Celsius, but when we do our calculations, it always has to be in Kelvin. And our standard pressure is 1 atmosphere of pressure. Internationally, there is moved toward using bars instead of atmospheres It has not caught on in the U.S., at least not yet. So our standard is still 1 atmosphere of pressure. If we're dealing with a gas where the volume is poorly defined, such as air, how do we describe the properties of air? What volume do we use? So since air doesn't have a defined volume, another way that we could write the gas laws is based on a molar volume. We could do V sub m for molar volume, and that is volume divided by moles, so liters per mole. So the atmosphere, the molar volume of that can change just depending on molar volume of that would not change. The molar volume of the atmosphere would not change whether we sample a liter or a cubic meter of the gas or a cubic kilometer of the gas. So if we put that into the ideal gas law, we get pressure times molar volume is equal to RT, the gas constant times Kelvin temperature. So PVM equals RT. Molar volume of a gas can also be calculated by molar mass of a gas divided by its density. So molar volume is going to have units of liters per mole. Molar mass is grams per mole. So if we want our units to cancel out, gas density has to be grams per liter. The molar volume of a gas does not change depending on the gas present for ideal gases. So all ideal gases have the same molar volume at standard temperature and pressure, STP. This molar volume is 22.41 liters per mole. So each mole occupies 22.41 liters. So it's 22.41 liters per mole. So non-ideal gases, which are called real gases, will deviate from this value to some degree. So we can use this relationship, STP molar volume, to convert between moles and volumes of gas when we are at standard temperature and pressure, STP. So that means volume is equal to 22.41 times moles, or 22.41 liters per mole is equal to volume divided by moles, liters per mole. So we derive the ideal gas law from the individual two property laws. And of course we can take the ideal gas law and convert it back into each of these. So if we take the ideal gas law, PV equals nRT, we're setting moles and temperature constant, so that means nRT is equal to a constant, so PV is equal to a constant. So that allows us to have initial PV equals final PV. It'll work for Charles' law, Gay-Lussac's law, Avogadro's law. All these will come out of the ideal gas law.